Okay, sometimes power series are used to approximate integrals that can't be integrated by hand easily, or some that cannot be integrated at all, by changing them again to a power series that will look like a sum of polys going on forever and ever. So let's look at this integral in power series form. When I look at 1 over 1 plus x to the 5th, there's no real or quick easy way that I can do this. There's no substitution that'll really work. I can't really do a trig sub of any form. So let's change this guy into its power series version. So I'm going to pull the integrand on this side, and I'm going to try to use our friend, that simple geometric series with 1 over 1 minus box business that we talked about. So let's go ahead and manipulate this to be able to use that. So now it becomes pretty evident what my box is. It looks like this is going to be the box I'm interested in. So I'm almost on my way to getting the power series for it. I have to ensure that this in absolute value will be less than 1. That'll be the radius of convergence. So it looks like between -1 and 1, this guy is useful for us. So if I am integrating, if I actually had limits of integration, this would be useful, of course, if my limits of integration were within my radius of, or my interval of convergence. So let's get rid of that negative here. Put it by itself, because less mistakes are made if you have x to be some positive term. So this is the power series representation for this function, and this function gets captured by this power series on this interval, and we looked at that in class graphically what it means, how this gets captured by this in this interval of convergence, -1 to 1. Now let's go put this back in here and try to integrate it, because now that's just going to be a polynomial that goes on forever and ever. So again, opening this up, we get an idea of what the polynomial looks like, and we could just go ahead and integrate this term by term as it is from here, or plug this whole guy back in here and then get it in terms of a summation notation. Okay, we put that guy back in there. That's going to give us from 0 to infinity. Again, I'm integrating, not differentiating, because remember when I differentiate, I upped 1 because the constant term gets wiped out. And here the only thing that I keep an eye on is the x's, because I'm integrating with respect to x, so I don't let the n's really bother me. So I have x to the up this by 1 and divide by it, just like you would in the past when you integrated. And don't forget it's plus some constant c as well. So if you were to spit the terms of this guy out, you would see that it turns out to be x minus, when n is 1, x to the 6th over 6. When n is 2, I get to the 11th over 11, and so on, which really captures this guy integrated. Actually not. Yeah, it is 11th to the 11th. Captures this guy if I were to look at it term by term. It's just integrating the guy term by term. So evaluating this integral using a power series really spits this guy out. And again, if I had limits of integration, they would be useful if they were in that interval of convergence. Outside of that, this does not get captured by this guy well, and so it wouldn't be useful. Actually, one thing I do want to point out, we sort of forgot to check, is that the radius of convergence after integrating would still be 1, like it was here. However, as we mentioned in class, the interval of convergence may change once you integrate. So for this guy, it's between -1 to 1. For this guy, I should really go check the endpoints to see what happens. I mean, it didn't ask for the interval of convergence, but let's just go ahead and see if it remains the same or if it changes. So for this guy, I got to go check the endpoints. So we'll check x equals -1 into that series and see what happens. And we'll quickly check x equals 1 to see what happens, just to get a quick idea of, did the interval of convergence endpoints change and remain the same? So to check the -1, I just put a -1 for my x. I left off the constant term because I just want to see if this thing by itself actually converges or not. So it looks like I have those -1 guys upstairs that I need to combine. So that'll be -1 to the, I guess, n and n. 5n will give me 6n. Same base, add the exponents over 5n plus 1. And if I'm looking at 6n plus 1, it looks like that guy is always going to be negative. Because all I'm doing is I am taking the n, multiplying it by 6 and adding 1, and that's always going to give me an odd exponent. So if it always gives me an odd exponent, then that guy is always going to remain to be negative, regardless of what n is. So I guess I might as well just write it like this, -1 on top with that other business, which clearly does not make it alternating. It just makes it a negative of this whole business. And this, by now, you should recognize if we do comparison test or a limit comparison test, this guy is going to be related to the harmonic series, and it's actually going to divert. So you can do that test on your own to ensure that you actually believe that, but this will end up diverging. Negative outside is not going to change anything. So x equals -1, still no good. Let's go check x equals 1. So where I had the x in my series, I went and put in the 1 this time. And it looks like the 1 doesn't really do anything. So I have an alternating series this time. And if I take this alternating series and look at all the positive terms, or look at all the terms in absolute value, in other words, and pull out my Bn, it looks like it's going to satisfy the two conditions of the alternating series test. Again, I will leave that for you to show. And so this guy actually converges at 1. So the interval of convergence is actually going to be -1 to 1 included for the guy that I ended up integrating. So here it was not included, but on this, for this one, 1 actually makes sense and converges. Let's look at another example. It says use differentiation to find a power series representation for this guy, for this function. Then use that, use that result to get one for this other function. So differentiation for this, and then it looks like, yeah, if I differentiate this, I am going to have a 1 plus x cubed popping out somehow. So let's go ahead and start with this one. Let's focus on that before we do the second part. So this is my destination, and the question I must ask myself is, what function should I come up with that when I differentiate it, I end up with this guy? So this guy, again, looks like it involves a 1 over 1 plus x, a version of our friend power series that's useful for us. So let's guess. Let's start with a guess of 1 over 1 plus x, because I know when we differentiate that, there's going to be a -1 exponent that's going to come down and then create a -2 exponent. So let's give that a try. So this is my guess. I'm thinking this will eventually get me to my destination with differentiation. So when I differentiate this guy, I end up with -1 over 1 plus x quantity squared, which really doesn't quite look like what my destination is. It's got that sign that it's off by. So I'm gonna, I like just adjusting my guess a little bit and throwing in a negative in there so that it can cancel and actually get me to where I should get to. So this negative is kind of, again, throwing me off. So I'm gonna say, let's use f of x equals -1 over 1 plus x. Because when I differentiate this, then for sure the negatives will cancel each other out, and I'm going to get the guy that is my destination. So let's go get a power series for this guy. So I pulled out the -1 by itself, turned it into something where we could use our friendly power series, the basic geometric one. I end up with -x to the n, and I'm going to split up the negatives and also move this guy, since it's to the power of 1, inside and make it merge with this guy. So I had n of these, I pulled in one more, so that makes it n plus 1. So now this is a power series representation of this for, of course, a radius of 1 around x being 0. So this guy is equal to this guy, and now we're going to go ahead and differentiate both sides with respect to x. So I rewrote this as -1 times this guy to the -1, and we differentiated it, and we ended up with exactly what we wanted, our destination, because we did that negative change for us. So now we have what we needed, and on the right we're going to have n equals 1 to infinity. Because we're differentiating, the first constant term is going to die down, bring down the n. Remember, you're only focusing on the things that have x's because you're differentiating with respect to x. So now you're going to have bring down the n and knock down the power by 1. This is where we're at. I'm going to do a quick index change on this guy just to have x to the n's involved only. So we will let all the n's go to n plus 1 so that we can have an x to the n on the right side. That's going to give me this guy over here, and that'll be subtract 1 from both sides. That's n equals 0, -1 to the n plus 1, n plus 1, and I have x to the n. So this guy has a power series representation as such on the right, with a radius of convergence of 1. Again, we could check the endpoints too, but it didn't ask for the actual interval. It just said get a representation for this, and that's what it should look like. Actually, I see something a little bit off here, because I did the index change, n plus 1 plus another one. Let's fix that. This went to n plus 1, and then there was another plus 1. So this guy actually ends up being n plus 2. But n plus 2, -1 to the n plus 2, is going to be the same as -1 to the n. Because if I'm at n equals, let's say, 0, this will be 1. And that'll be also even, and it'll be 1. If I'm at n, let's say, equal to 1, this will be odd power. That would be a -1. And 1 plus 2 will make that an odd power and stay a -1. So evens and odds act the same for these two guys. So why don't we just get rid of this and call it a simple -1 to the n? That looks cleaner. So again, I repeat, when I did the index change, I had forgotten to do it here. I changed that, it went to an n plus 2, but then I said might as well just use -1 to the n. So instead of doing the second part where we were supposed to use this, we'll do that in the next video. Let's go look at a graphical representation of this as well. This function looks like this power series on a radius of convergence of 1 about the center, which is 0. I just went ahead and opened this up, so this is the first partial sum. Just a constant, y equals 1. Let's go graphically see what happens. I'm looking at that function centered at 0. If I look at the first partial sum, that's all it looks like. Pretty bad approximation, just good, add 0. If I want to go and I want to look at the second partial sum, 1 minus 2x, I'm going to get all confused once. Okay, I'm back where I wanted to be. So now I'm going to go change and look at 1 minus x. That's a better approximation because it matches up with the slope of the guy acting the same way. 1 minus 2x, just a linear function. Let's go to the quadratic one, 3 of them, so a second degree polynomial, and see what it looks like. Second degree polynomial. That definitely looks better. It captures more of the curve. Let's go to a third degree. Shoots down, captures a little bit better. Fourth degree, even better than before. Fifth degree, shoots down. Sixth degree, and so on. Notice this is the actual curve in purple, and the one in blue is my polynomial approximation. And in this window between -1 and 1, it's capturing my curve pretty well. So we know that we found a pretty decent power series representation for it. The one that we were asked to find actually matches up graphically. So in the process, I didn't make any mistakes or anything.